Time dilation. When people imagine time travel, they usually think of sci-fi, stepping into a machine, pressing a button, and suddenly waking up in the past or future. But here's the twist. Time travel isn't just fantasy. It's already real. Not the flashy, visit your grandfather kind, but the scientific, proven kind, time dilation. Einstein's theory of relativity tells us that time isn't fixed. It bends, stretches, and ticks differently, depending on how fast you move and how close you are to massive objects. The faster you go, the slower your clock runs compared to someone standing still. The deeper you sit in a gravitational field, the slower your seconds tick compared to someone far away. This isn't theory anymore. It's been tested again and again. In 1971, scientists Hoffele and Keating flew atomic clocks around the world on commercial airliners. When they brought them back and compared them to stationary clocks, the airborne ones were off by exactly the amount Einstein predicted. Even today, GPS satellites orbiting Earth need constant corrections for both velocity time dilation and gravitational time dilation. Otherwise, your phone's map would drift by kilometers every day. And it gets even stranger. High-energy muons, particles created when cosmic rays hit Earth's atmosphere, should decay in microseconds. Yet when traveling near light speed, their clocks slow down, letting them survive long enough to be detected at the surface. So yes, astronauts on the International Space Station are technically time travelers. They orbit Earth at 28,000 kilometers per hour, and when they return, they're a few milliseconds younger than they would have been on the ground. Tiny differences, sure, but real. Scale that up to near light speeds. Or park yourself near a black hole, and you could leap centuries into the future while only experiencing a few years. Time dilation proves the future is already accessible. The past may be locked away, but the fast lane forward is wide open. If you want to see tomorrow's world, all you need is speed, gravity, and patience. The twin paradox. Imagine two twins. One stays on Earth, the other boards a spaceship, accelerates to near the speed of light, and takes a long journey through space. When the traveling twin comes back, something bizarre happens. They're younger than the twin who stayed home. That's the legendary twin paradox. At first glance, it feels like a contradiction. If motion is relative, shouldn't each twin see the other as moving? Shouldn't each claim the other's clock is running slow? That's the paradox. But the truth is, there's no real paradox at all. The difference comes from acceleration. The Earth twin stays in one frame of reference, while the space twin has to accelerate, turn around, and decelerate to return. That breaks the symmetry. Relativity predicts that the traveling twin genuinely experiences less time, and experiments back it up. This isn't just a thought experiment anymore. It's been tested on smaller scales. Astronauts orbiting Earth on the ISS experience time dilation. They age ever so slightly less than people on the ground. GPS satellites, zipping around Earth at high speed and sitting higher up in weaker gravity, also experience time at a different rate. Engineers constantly correct for this, or else GPS would drift completely off course. Even high-speed jets with atomic clocks have confirmed the effect. So in the end, the twin paradox isn't really a paradox. It's a preview. It shows us that the future is, in a sense, already reachable. If you could travel near light speed and come back, Earth would have aged decades, centuries, or even millennia, while you'd only have lived through a few years. It's not sci-fi, it's physics. The twin paradox proves a strange truth. Time is not universal. Your seconds are not the same as mine, and under the right conditions, they can stretch apart in spectacular ways. Closed time-like curves, CTCs. So far, time dilation only sends us forward, but Einstein's equations don't stop there. Under certain exotic conditions, general relativity allows for something far stranger, closed time-like curves, or CTCs. In simple terms, a time-like curve is just the path through space and time that an object takes. For you, it's walking to the kitchen while time ticks forward. For a planet, it's orbiting the sun while time moves on. But relativity's math admits special solutions where that curve closes back on itself. Translation. You move forward in time and space, yet eventually loop back to the very point where you started. A time machine, written into the geometry of the universe. These solutions don't show up in our everyday world. You don't trip into a time loop walking to the store. But when physicists play with Einstein's equations under conditions like rotating universes, infinitely long cylinders, or warped spacetimes, they find CTCs pop out naturally. Gödel's rotating universe is one example. Tipler's cylinder is another. And wormholes with certain tweaks can generate them too. If CTCs exist, the implications are enormous. It would mean the laws of physics allow travel not just into the future, but back into the past. You could revisit yesterday, change events, or get trapped in paradoxes. It's the kind of concept that turns time from a one-way street into a looping roller coaster. But here's the catch. Just because relativity's math permits, it doesn't mean nature does. Building a real CTC usually requires impossible conditions, like infinite cylinders or exotic negative energy. Plus, the moment you let CTCs exist, you open Pandora's box of paradoxes. Still, the fact that CTCs appear at all is astonishing. Einstein's own equations whisper the possibility that time might not be as linear as we think. They're the mathematical doorway into the past, waiting to see if reality ever lets us walk through. Gödel's rotating universe. In 1949, Kurt Gödel, the same Gödel famous for his incompleteness theorems in mathematics, dropped a bombshell in physics. He found a new solution to Einstein's equations of general relativity, a rotating universe. And not just any rotating universe, one where time itself could loop back on itself. Gödel's universe was filled with matter that rotated on a cosmic scale. In this model, space and time are so twisted by this rotation that you can take a path through space-time, always moving forward in your own timeline, and eventually circle back to your own past. In other words, Gödel had mathematically created a universe with natural closed time-like curves built right in. At first, physicists didn't know what to make of it. Gödel wasn't even trying to solve time travel. He just wanted to show off how weird general relativity could be. But his solution stunned Einstein, who reportedly wasn't too happy about it. It implied that relativity allowed universes where causality, cause and effect, could break down completely. So, could our universe be like Gödel's? Thankfully, no. Observations show our cosmos is expanding, not rotating. There's no evidence for the kind of cosmic rotation his solution requires, but that doesn't make it irrelevant. Gödel's model was the first real proof that general relativity doesn't automatically forbid time travel. It cracked open the door and showed that going back wasn't just science fiction. It was mathematically possible. Of course, it comes with problems. A rotating universe would wreck the very idea of universal time. There'd be no agreed upon now anywhere, and paradoxes would be everywhere. But Gödel's rotating universe remains a milestone, a reminder that the rules of time might be more flexible than our intuition wants to admit. Gödel's work proves something shocking. If the universe had been just a little different, time travel wouldn't be a dream. It would be the normal state of reality. Tipler's infinite cylinder. Imagine a massive cylinder, so dense it's made of neutron star material, spinning at nearly the speed of light. This is the basis of physicist Frank Tipler's thought experiment from the 1970s, known as the Tipler cylinder. According to general relativity, such an object could twist space-time so severely that closed time-like curves would form around it. Translation: fly your spaceship in just the right path around the cylinder, and you could loop back into your own past. The idea comes from something called frame dragging, which we already know is real. When massive objects rotate, they drag space-time around with them. Earth does it a tiny bit, and satellites have actually measured the effect. Now imagine scaling that up with an infinitely long, incredibly dense cylinder. The rotation would drag space-time so violently that time itself could curl into loops. Sounds amazing, right? But here's the catch. It only works if the cylinder is infinite in length. If it's finite, the math breaks down, and the time-traveling curves don't appear. And as much as physicists love big ideas, building an infinite spinning cylinder of neutron star matter is, well, not exactly practical. Even with a finite cylinder, you'd need something impossibly long, tens of light years, and it would collapse under its own gravity before it could ever spin that fast. Still, Tipler's cylinder is important because it showed that general relativity doesn't just allow time travel in strange universes, like Gödel's. It allows it in specific engineered setups. In theory, with the right arrangement of mass and motion, humans could build a time machine. In practice, the energy requirements and stability issues make it absurdly impossible. But the lesson remains. Relativity keeps tempting us with loopholes. The Tipler cylinder may be a fantasy, but it's a fantasy written in the same math that describes black holes and gravity itself, and that makes it hard to ignore. Cosmic strings and the Gott loop. Back in the 1980s and 90s, physicists began to seriously consider the idea of cosmic strings, not literal strings, but ultra-thin defects in spacetime that could have formed in the early universe, like cracks in ice as it freezes. A cosmic string would be thinner than an atom, but incredibly dense, with a single kilometer weighing more than Earth. They're purely theoretical, but if they exist, they'd be among the most extreme objects in the cosmos. Now here's where it gets wild. In 1991, physicist J. Richard Gott showed that if two cosmic strings zipped past each other at nearly the speed of light, they could warp spacetime enough to create a closed time-like curve, essentially a loop in time. Ride a spaceship around the right path, and in principle, you could arrive back before you left. That setup is called the Gott loop. On paper, it works. The math checks out in general relativity, but reality isn't so generous. First, we've never actually detected a cosmic string. Decades of searching with telescopes, gravitational wave detectors, and cosmic background studies have all come up empty. If they exist, they must be exceedingly rare, or much weaker than expected. Second, even if they did exist, arranging two of them to pass each other at nearly light speed in just the right way is absurdly impractical. We're talking about manipulating cosmic scale objects with energies far beyond anything imaginable. Still, the Gott loop is fascinating because it shows how even hypothetical relics of the early universe could, in principle, bend time into a circle. It's another reminder that Einstein's equations don't slam the door on time travel. They keep leaving it cracked open, daring us to wonder. Cosmic strings may never be found, and the Gott loop may remain pure speculation. But as long as the math works, it sits there in the catalog of cosmic what-ifs, an impossible dream written into the geometry of the universe. Traversable wormholes and time shifts. If black holes are the universe's traps, wormholes are its shortcuts. In theory, a wormhole is a tunnel through spacetime, an Einstein-Rosen bridge that connects two distant regions of the universe. You step in one mouth, step out the other, and suddenly, you've crossed light years in a blink. It sounds like fantasy, but the math of general relativity allows them. The problem is making one traversable. Most wormholes, if they exist, collapse instantly, or are sealed off behind event horizons. But in the 1980s, Kip Thorne and Michael Morris showed that if you could hold a wormhole open with the right kind of exotic matter, something with negative energy density, then it might stay stable long enough for travel. Suddenly, wormholes went from science fiction plot devices to serious physics papers. Now here's where time travel sneaks in. Imagine you create a wormhole with two mouths. Keep one mouth near Earth and take the other on a high-speed journey, close to light speed, then bring it back. Thanks to time dilation, the traveling mouth experiences less time than the stationary one. Reconnect them, and now you've got a time offset. Step through the younger mouth, and you pop out of the older one, effectively traveling into the past. It's elegant, it's terrifying, and it's loaded with problems. For one, negative energy isn't something you can just scoop out of a bottle. Quantum effects like the Casimir effect show it can exist, but only in tiny amounts. You'd need a planet's worth just to keep a wormhole big enough for a person open. And then there's stability. Any stray radiation or particle falling in could destabilize the whole thing, snapping it shut violently. Still, traversable wormholes remain one of the most compelling time travel concepts. They don't break relativity, they use it. They offer a way to build a machine where past and future connect. And even if they're forever out of reach, they're proof that the universe's own equations allow for tunnels not just across space, but across time. Negative energy. If wormholes are the highways of time travel, then negative energy is the fuel you'd need to keep them open. The problem is, it's a fuel that barely exists, and when it does, it's in the tiniest possible doses. Normally, energy is always positive. Mass, light, motion, they all add up. But in quantum physics, strange exceptions show up. The most famous example is the Casimir effect. Put two uncharged metal plates very close together in a vacuum, and quantum fluctuations of empty space push them together. Between the plates, the energy density is actually lower than in the surrounding vacuum, effectively negative. It's a real, measurable phenomenon. That's exciting, because negative energy is exactly what theorists like Kip Thorne showed you'd need to hold a wormhole open or to make a warp drive work. Positive energy curves space-time inward, like gravity pulling things together. Negative energy curves space-time outward, pushing instead of pulling. In principle, enough of it could stabilize a wormhole or create a bubble that bends time itself. But here's the catch. Quantum field theory slams on the brakes with what are called quantum inequalities, worked out by Ford and Roman. These rules basically say you can't have large amounts of negative energy hanging around for long. It can appear, but only briefly, and the bigger the effect, the shorter its lifespan. You might get tiny flashes in controlled setups, but the idea of storing planet-sized quantities to build a time machine, nature seems to forbid it. Even if you could somehow harness negative energy, there's the stability problem. Exotic matter might help balance a wormhole, but the slightest fluctuation could collapse it, or worse, unleash a runaway effect. Think of it like balancing a pencil on its tip. Negative energy proves a point. The physics of time travel isn't just about imagination. It collides with hard limits. The universe dangles the possibility in front of us, but every time we reach for it, quantum mechanics yanks it away. The Alcubierre warp drive. In 1994, physicist Miguel Alcubierre published a paper that sounded like pure science fiction. He showed that general relativity's equations allowed for something astonishing, a warp drive. Not faster than light travel in the traditional sense. Einstein's speed limit still holds, but a clever workaround. Instead of moving a ship through space, you move space itself around the ship. The idea works like this. Behind the spacecraft, space-time expands. In front of it, space-time contracts. The ship sits in a warp bubble, never actually moving faster than light relative to the space around it. But because the bubble itself can surf across the universe, you could effectively travel light years in weeks, or even days. And here's the kicker. Some versions of the warp bubble allow for closed time-like curves, which means you could use them not just for fast travel, but for time travel. It sounds incredible, but of course, there's a catch. The same one that haunts wormholes. The Alcubierre drive requires negative energy to work, and not just a little. Early estimates said you'd need more energy than exists in the observable universe to power one. Later refinements reduced that requirement, but it's still astronomically beyond anything humanity could ever hope to produce. And that's before you even worry about stability. There's also a serious problem with causality. Some warp drive setups let you create loops in spacetime, meaning paradoxes galore. Stephen Hawking once argued this was exactly why warp drives would never be physically realized. The universe protects itself from time travel violations. Still, the Alcubierre drive remains one of the most tantalizing concepts in physics. It doesn't break relativity. It uses relativity in a clever way. It dangles the possibility that the stars might not be out of reach forever, and that time itself might be more flexible than we think. For now, though, it lives where so many time travel ideas live, on the razor's edge between what's mathematically possible and what's physically impossible. Kerr black holes. Most people picture black holes as bottomless pits where nothing escapes. That's true for the simplest kind, non-rotating Schwarzschild black holes. But real black holes in the universe spin, and spin changes everything. Enter the Kerr black hole, a solution to Einstein's equations discovered in 1963. A Kerr black hole isn't just a point. At its center is a ring singularity, a loop of infinitely dense matter. Around it are two event horizons. An outer one, like a normal black hole's point of no return, and an inner one that leads to bizarre territory. Between them lies the ergosphere, a region where spacetime itself is dragged around so violently that nothing can stay still. Here's where it gets crazy. The math says you could, in theory, pass through the ring singularity and emerge elsewhere, not just in space, but in time. Hidden inside are regions called acausal zones, where closed time-like curves naturally form. In principle, a spaceship could dive in, loop around, and come out in the past. Sounds like the ultimate time machine, right? Not so fast. These interiors are unstable. Physicists discovered something called mass inflation. As matter and radiation fall inward, they pile up infinitely at the inner horizon, turning it into a deadly wall of energy. In other words, any real traveler would be fried long before reaching those acausal zones. On top of that, there's cosmic censorship, the idea that nature hides singularities behind horizons, preventing the universe from revealing its most dangerous secrets. Still, Kerr black holes are fascinating because they show how relativity keeps teasing us. Spin a black hole fast enough, and you don't just get weird physics, you get a doorway to potential time loops. Whether those doorways are forever blocked by instability or not, the equations are clear. Deep inside rotating black holes, the normal rules of cause and effect may simply break down. Kerr black holes remind us that time travel doesn't just belong in theory papers. It might already be lurking in the hearts of the universe's darkest monsters. Tachyons and the Anti-Telephone. Einstein's theory sets a hard limit. Nothing with mass can reach or exceed the speed of light. But what if something started out faster than light? Enter the tachyon, a hypothetical particle that always moves faster than light. It's never been observed, but the math allows for it. Sort of. Tachyons would be bizarre. For one, instead of needing energy to speed up, they'd actually need infinite energy to slow down to light speed. They'd always be superluminal, forever outracing photons. At first, they seemed like harmless curiosities in equations. But then physicists realized something chilling. If tachyons exist, they could break causality. Here's how. Imagine you send a tachyon signal to a friend moving relative to you. Because of relativity, in your friend's frame of reference, that signal might arrive before you even sent it. Now chain this together. Your friend sends a tachyon back, and suddenly, you've built what's called a tachyonic anti-telephone, a device that lets you send messages into the past. Ask a question, and get the answer before you ever asked it. Cause and effect flip upside down. This is why most physicists doubt tachyons are real. If they exist, our entire framework of causality crumbles. It would mean paradoxes everywhere. Lotteries won before tickets are bought, warnings received before disasters happen. To preserve consistency, most theories treat tachyons as mathematical ghosts, signals that show instability in a model rather than real particles. But the idea lingers because it's a reminder of how fragile causality is. The speed of light isn't just a speed limit, it's the wall that keeps past and future from bleeding into each other. If anything could break that wall, time itself could come unglued. Tachyons may never be found, but the anti-telephone thought experiment proves one thing. Faster than light travel and time travel are deeply entangled. If you allow one, you almost always invite the other. Novikov Self-Consistency. Whenever time travel comes up, the same nightmare pops into everyone's head, the grandfather paradox. What if you go back in time, prevent your grandparents from meeting, and erase your own existence? If you never existed, how did you travel back in the first place? Loops like this threaten to rip logic apart. Enter the Novikov Self-Consistency principle, proposed by Russian physicist Igor Novikov in the 1980s. His idea is simple but radical. If closed time-like curves exist, then the only possible events are ones that are self-consistent. In other words, you can't create paradoxes. The universe won't allow it. Take the grandfather paradox. Under Novikov's rule, any attempt to stop your grandparents from meeting would fail. Maybe your gun jams, or you slip, or you end up becoming the very reason they met. Whatever happens, history stays consistent. You can travel into the past, but you can't change it. You were always part of it. This sounds restrictive, but it doesn't make time travel boring. It just means your actions in the past are already baked into history. In fact, it can lead to strange bootstrap scenarios, where information or objects loop through time without ever being created. A physicist gets a set of equations from his future self, publishes them, and then hands them back to his younger self decades later. Where did the equations come from? Nowhere. They just exist in a closed loop. Not everyone buys into Novikov's principle, but it does neatly solve paradoxes without breaking physics. If time travel is real, then free will might not work the way we think. You could act in the past, but only in ways that keep history intact. The Novikov principle reminds us of a sobering truth. If time travel ever exists, it may not give us freedom to rewrite history. Instead, it could trap us in a loop where every choice we make was already made long ago. Many worlds, branching timelines, If Novikov's principle says the past can't change, the many worlds interpretation flips that idea on its head. Instead of one unbreakable timeline, reality branches. Every choice, every quantum event, every possibility spawns a new universe. Apply this to time travel, and paradoxes vanish. Go back and prevent your grandparents from meeting? Fine. You just created a new branch where you were never born. But your original timeline, the one where you did exist, keeps chugging along untouched. The universe doesn't stop you, it simply forks. This idea comes from Hugh Everett's interpretation of quantum mechanics in the 1950s. While originally meant to solve quantum measurement puzzles, it fits perfectly into time travel storytelling. Movies like Avengers, Endgame lean heavily on this model. Change the past, and you don't rewrite history. You just make a new one. But does physics really support this? That's still debated. Many Worlds has serious fans in quantum foundations, but whether it applies to macroscopic time machines is an open question. Critics argue that creating whole new universes on demand sounds extravagant. Supporters counter that the math of quantum mechanics already implies branching, whether we like it or not. From a paradox perspective, Many Worlds is elegant. It allows freedom. You can change the past without breaking causality. No jams, no forced outcomes. But it comes at a cost. You can never change your own past. If you went back to save a loved one, you wouldn't alter the timeline you came from. You'd just spin off a copy where they live. Your home timeline remains unchanged. The Many Worlds picture makes time travel feel less like editing history and more like navigating a multiverse. Every jump creates another strand in an infinite cosmic braid. Whether that's real physics or just clever storytelling is still an open mystery. But if the universe truly branches, then every impossible paradox already has an escape hatch, sitting in another world next door. Hawking's chronology protection. By the early 1990s, physicists had piled up too many what-if time travel scenarios. Wormholes, warp drives, cosmic strings, Tipler cylinders. On paper, general relativity seemed full of loopholes that bent time into loops. But Stephen Hawking wasn't buying it. In 1992, he proposed the chronology protection conjecture, a built-in rule of the universe that prevents time machines from ever forming. Hawking's argument centered on quantum mechanics. Even if relativity's math allows closed time-like curves, he suggested that quantum effects would rise up and destroy them before they could stabilize. Imagine trying to build a wormhole and turn it into a time loop. As soon as you get close, quantum fluctuations, tiny bursts of energy that always exist in empty space, would amplify uncontrollably. Radiation would pile up around the wormhole throat or inside the warp bubble until it collapsed violently. The universe would protect causality by nuking your time machine the instant you tried to activate it. It's like nature has a cosmic firewall. You can dream about paradoxes, bootstrap loops, or rewriting history. But the laws of physics step in and say, no. The idea fits with what we've seen so far. Every serious time machine concept requires conditions that are absurdly impractical. Exotic matter, infinite cylinders, cosmic scale manipulations. None of them look remotely buildable. Maybe that's not an accident. Maybe reality is fundamentally allergic to time machines. Hawking himself joked that this was why we don't see hordes of tourists from the future. If time travel were possible, someone would have shown up by now. The silence, he argued, is the best evidence that chronology protection is real. Of course, it's still a conjecture, not a proven law, but it remains the leading attitude among physicists. The math of relativity may tempt us with time travel, but quantum mechanics slams the door shut. In short, history is safe, not because paradoxes are impossible to imagine, but because the universe has a built-in security system that won't let them happen. Quantum CTCs. General relativity might allow closed time-like curves, but what happens when you throw quantum mechanics into the mix? In the 1990s, physicist David Deutsch proposed a radical idea: quantum CTCs. Instead of paradoxes tearing the universe apart, he argued that quantum mechanics could enforce consistency in a weird but logical way. delay. In Deutsch's model, a particle traveling back in time must enter a fixed point state. That means its past and future versions line up perfectly, so no contradictions can occur. Even if you try to create a paradox, the math adjusts probabilities until everything stays consistent. The result? A time traveler who always does things that fit the timeline, just like Novikov's principle, but with quantum probability doing the heavy lifting. This sounds neat, but it comes with bizarre consequences. Quantum CTCs would let you do things normally forbidden, like perfectly cloning an unknown quantum state. They'd also allow for supercomputers that solve problems instantly by trying every possibility in a looped timeline. Basically, they'd turn physics into cheat codes. Not everyone agrees with Deutsch. Another approach, called post-selected CTCs, or PCTCs, suggests a different mechanism. Instead of forcing fixed points, PCTCs rely on quantum teleportation combined with post-selection, throwing out outcomes that would cause paradoxes. The idea is that only consistent histories survive, while contradictory ones simply never occur. Here's the kicker. Deutsch CTCs and PCTCs don't agree. They make totally different predictions about what would happen if you could really build a time machine. One says paradoxes get smoothed over by probability. The other says paradoxes just vanish because only self-consistent histories are allowed. Neither model has been proven, of course, but physicists have run small-scale simulations of these ideas using quantum circuits, trying to mimic time travel logic in the lab. The results are fascinating, but they don't prove time travel exists. They just show how quantum mechanics might behave if it did. Quantum CTCs remind us of something crucial. Time travel isn't just about rockets and wormholes. It's about the deepest rules of reality and whether quantum probability itself might bend to protect causality. Retrocausality and delayed choice. Experiments. In classical physics, cause comes before effect. You drop a glass, then it shatters. But quantum mechanics? It loves to mess with our intuitions. Some experiments suggest that, at the microscopic level, the future might influence the past. This strange idea is called retrocausality. One of the most famous examples is Wheeler's delayed choice experiment. Imagine light passing through a double-slit setup. Normally, if you measure which slit the photon goes through, you kill the interference pattern. But if you delay that measurement, decide at the last possible second whether or not to check, the photon seems to know what you're going to do. It behaves as if your future decision reaches backward in time and affects its past path. Things get even weirder with the quantum eraser experiment. In these setups, information about a particle's path can be erased after it's already been detected, and yet the interference pattern returns as if the earlier event was rewritten. To many people, it looks like the future is tinkering with the past. So is this time travel in action? Not really. The key is that while these experiments look retrocausal, they don't allow you to send usable information to the past. You can't set up a quantum eraser to send lottery numbers back in time. The weirdness comes from entanglement and probability, not from actual causal loops. Still, these experiments hint at something profound. The flow of time in quantum mechanics isn't as rigid as we experience it. The before and after that define our everyday lives blur at the quantum level. Some physicists argue that this could point to a deeper, time-symmetric reality, where cause and effect are emergent illusions, not fundamental laws. Retrocausality won't give us paradoxes or time machines, but it keeps the dream alive by showing us that time itself may be stranger than we think. If the universe already lets the future whisper to the past in subtle ways, who's to say it can't shout someday? Arrows of time. Look around you. Coffee cools down, people age, glass shatters. Time feels like a one-way street, always pushing from past to future. But here's the puzzle. The fundamental laws of physics don't care about direction. Newton's equations, Maxwell's equations, even quantum mechanics, they all work just as well if you flip time. So why do we experience such a strong arrow of time? The leading explanation comes from entropy, the measure of disorder. The second law of thermodynamics says that in a closed system, entropy tends to increase. An egg can scramble, but never unscramble. A cup can break, but never reassemble. That rising entropy gives time its direction. But this just pushes the mystery deeper. Why was entropy so low in the early universe to begin with? That's where the past hypothesis comes in. It suggests that the Big Bang started in an extraordinarily ordered, low-entropy state. From that cosmic starting point, entropy has been climbing ever since, creating the arrow of time we experience. Without that special initial condition, there might be no difference between past and future at all. There are other arrows too. The cosmological arrow points forward because the universe itself is expanding, not contracting. The psychological arrow ties in with memory. We remember the past, but not the future, likely because memory formation itself depends on entropy increase. Even in particle physics, we've seen tiny violations of time symmetry in certain decays, but nothing strong enough to explain the macroscopic flow of time. Here's the unsettling part. The arrow of time might not be fundamental. It could be a byproduct of cosmic history, a fluke of initial conditions. If the universe began differently, time might not feel like it flows at all. So while time machines spark our imagination, the bigger mystery might be this: why do we feel time moving forward in the first place? Until we understand the arrow of time, all talk of traveling through it is like trying to steer a river without knowing why it flows. Can we test a time machine? All these ideas, wormholes, warp drives, cosmic strings, sound thrilling on paper. But science isn't just about equations. It's about what can actually be built, measured, or tested. So, what happens when we run time machine concepts through the filter of practicality? The first roadblock is energy. Traversable wormholes require exotic matter with negative energy on astronomical scales. The Alcubierre warp drive, in its original form, demanded more energy than exists in the observable universe. Later refinements lowered the bar, but even the cheap versions still ask for amounts beyond anything humanity could dream of producing. Then there's stability. Wormholes collapse if even a single stray particle falls in at the wrong time. Kerr black holes look promising on paper, but the moment you try to pass the inner horizon, the buildup of radiation creates an impassable wall of destruction. The universe seems to punish any attempt to exploit loopholes. Even if you hand-wave away energy and stability, quantum back reaction looms large. Hawking's chronology protection suggests that radiation and quantum fluctuations pile up whenever you try to form a closed time-like curve, shutting it down before paradoxes arise. Time machines may simply self-destruct at the moment of creation. That hasn't stopped scientists from poking at the problem in clever ways. In quantum computing labs, researchers simulate toy versions of time travel by designing circuits that behave like closed time-like curves. These experiments don't build a time machine, but they let physicists test how information might behave in paradoxical scenarios. The results show that quantum mechanics has surprising ways to resolve contradictions, but they're still only analogies, not the real thing. So, can we test a time machine? Not in the literal sense. Not yet. Every serious proposal either collapses under its own requirements or breaks down under quantum effects. But the attempts aren't wasted. Each failure teaches us more about the boundaries of physics, sharpening our understanding of energy, gravity, and causality itself. In the end, the biggest constraint may not be technology. It may be the universe itself whispering, not here, not now, maybe never. Ethics and paradoxes in practice. Suppose tomorrow we crack the code, wormholes stabilized, paradoxes resolved, and a working time machine humming in a lab. The physics questions might end, but the ethical nightmares would just begin. First, causal safety. Who decides what's safe to change? Even if Novikov's principle or many worlds interpretations apply, messing with timelines risks collateral damage. Entire realities spun off or erased by a single careless choice. Second, information hazards. A time loop could create bootstrap objects, technology, formulas, even entire books that have no inventor. Who owns an equation that was passed backward from the future? Could someone patent knowledge that technically never had an origin? Third, weaponization. A government or corporation with access to controlled time loops could outmaneuver rivals endlessly, predicting every move before it happens. The first nation to master time travel wouldn't just rule the world, they'd rule history itself. And then there's the psychological toll. Imagine knowing every action you take was already decided, or realizing that your attempt to save someone only creates the tragedy you were trying to avoid. Time travel doesn't just challenge physics, it shreds free will. Most physicists think we'll never face these dilemmas because time machines will never leave the pages of theory. But that doesn't make the questions less important. Grappling with them forces us to confront why we're so obsessed with time travel in the first place. At its core, time travel is about control, the desire to rewrite mistakes, relive glory days, or leap forward to a better world. Physics may never allow it, but the fantasy will never die. Because time isn't just a dimension we move through. It's the story we're trapped inside. And who wouldn't want the power to edit their own story?